Hello, this is Ms. Nichols, and this video is on charging, specifically how do objects end up with an unbalanced sigma charge. In previous physics classes, you should have learned about the basic principles of conservation, and we've talked specifically about conservation of mass and conservation of energy. So those are items that cannot be created or destroyed. The amount that the universe has will always have, nothing can change. The same is true for charge. So the basic tenet is that the total sigma charge in any closed system is going to be constant or conserved. We can't add or take away charge from any closed system. Now, in the biggest possible system, which is a system containing the entire universe, physicists believe that there just happen to be exactly as many protons as there are electrons. This is a massive coincidence. There's nothing that says that this has to be true based on Big Bang or any of those kinds of theories. There's no reason why we have the same number of protons or electrons, but it's a really good thing we do, because if we had an unbalanced amount of sigma charge, stars, planets, people would never have formed, because mostly those things have come together through the gravitational force, and as we learned about in the last slideshow, gravity is actually really weak compared to the electric force. So let's say we had a universe with a whole bunch of extra protons or electrons. Well, since extra protons will repel each other, basically what that's going to do, instead of allowing gravity to bring together stars and planets, is it's going to repel all of the dust in the universe from all the other dust, and it's going to basically prevent anything from ever forming into a solid single object. So it's a good thing that we ended up this way, but there's no real physics yet that will explain that that had to be the case. This means that the net charge, or the sigma charge of the universe, is 0, because we have exactly as many positive charged objects as we do negative. Another way to say this is that the universe is neutral. So this slideshow is going to be primarily focused on charging, which is the idea that most things start with balanced numbers of electrons and protons. An atom in its sort of most stable state usually has the same number of protons and electrons, which means that most atoms are neutral. Sigma q, which is the sum of the charges, is 0, because all the positive protons are canceled out by the negative electrons. And charging is defined as allowing objects as sort of to act like open systems, allowing electrons to move in or out of those objects, changing the sigma q of each object, and we call this charging. In general, we're not going to allow our protons to move, as we discussed in the last slideshow. They're kind of locked into the nucleus of an atom. If we yank a proton out of the nucleus, that's called a nuclear explosion. So while there are occasionally free-floating protons, charging never happens by moving protons. We always only do charging by moving electrons in or out of systems. So the sigma charge of a system is just the total, that means just the total, and that's basically add up all the protons and then add up the charge of the electrons, which is a negative number. So if we had this system with 4 protons in it and only 3 electrons in it, we would say the sigma q of that system is +1 e, e being the fundamental unit of charge, so the charge of a single electron. So the charge here overall is a very small amount of positive charge. In this system, where we have 4 protons and 4 electrons, sigma q would be 0. We also describe that as neutral. And in this system, we have 4 protons and 9 electrons. We would say the sigma q of that system is -3e, which is a larger negative charge. Over the course of the rest of the video, we're going to talk about some charging mechanisms and processes that you need to be able to explain how they happen and what the kind of results of them are. So the 3 charging mechanisms are: number 1, friction charging. This is a charging mechanism that always occurs between 2 insulators. Number 2 is called contact charging. This only occurs between 2 conductors. And number 3 is called induction charging. And for that kind of charging, we need at least 1 conductor, and the other one can be either a conductor or an insulator. There are also 2 processes that you should understand. You'll understand that, and we'll go into the details of that in just a minute. Those are called grounding, which you may have heard of before, and something called polarization. If you did the optics unit already, we talked about polarizing. This is a totally different kind of polarizing, so just understand this is electrical polarization. All right. So the first charging mechanism is called friction charging, and this occurs when you rub two different insulators together. In that process, transferring electrons from one to the other. So let's say we have an orange insulator and a blue insulator, and they are going to start off neutral, which means they have the same number of protons and electrons. And you'll notice that those are insulators because the electrons sort of like to stay close to their atom, and the sigma q for both of these is 0. But when you rub them together, something interesting happens. You're basically bringing the atoms on the surface of each of those substances really close in contact with the atoms of the other object, so much that they're kind of, their electron clouds are going to overlap temporarily. And when you do that, if you rub these things together a lot with a lot of friction, you provide an opportunity for one of those insulators to kind of grab and snag electrons from the other. We'll talk about why in just a minute. But when you're done, you'll notice that electrons have moved from one to the other. So if you do your sigma q after the charging process, you'll discover your orange one now has 5 extra protons, so it has a charge of positive 5e, and the blue one has 5 extra electrons, so it has a charge of negative 5e. You'll also notice that those electrons were stolen from the surface that was rubbed, right? They didn't really affect the electrons in the middle of that insulator because they can't move around within that insulator. And on the other object, the electrons that were kind of snagged remain pretty much on the surface or at the position of the friction for that blue insulator as well. One last little note about this, charge in the universe is conserved, which means that if we include these guys together in a single system, the sigma q for that system is 0 both times, before and after. They've just moved around to different objects within that system. So the property of the material that determines whether it is going to add electrons or lose electrons is known as the electrostatic series. And it's basically an experimental variable. People have determined it by rubbing things together and finding out which things ended up positive and which things end up negative. Fundamentally, it depends on the orbital dynamic or structure of the orbitals and the location of all the valence electrons. It's pretty complicated, but you can't necessarily predict, especially for really complex molecules like you find in rubber, plastic, etc., what the ultimate electrostatic value is going to end up being without just rubbing in other things and finding out. So here's a rough list of some common objects and where they tend to end up in terms of friction charging. So rubber, when you rub rubber on almost anything else, rubber really, really likes electrons and it ends up stealing the electrons. So it becomes negative very easily. Plastic also tends to become negative. Cotton and fur are insulators, but they're kind of more in the neutral zone. But of course, if you rub them on rubber, they're going to end up positive because someone has to lose the electrons. And then at the far other end, we've got, wool, glass, acetate, etc. Those tend to give up their electrons easily and become positive. So it's all about where the two objects are relative to each other on this electrostatic series to determine who ultimately ends up positive or negative. The same object could become positive when you rub it on one thing and become negative on another thing, depending on what those other objects are. The second kind of charging is known as contact charging, and this happens when we take two conductors that have different sigma charges and bring them into contact. If those conductors are identical, then the electrons are going to move until both conductors have the same sigma charge. So, for example, if I had these two conductors, this reddish one, this bluish one, that are identical sized, but they have different sigma charges to start. So the red one has 6 extra electrons, it's got a charge of plus 6e, and the blue one has 2 extra electrons, a charge of, protons for both of those, 6 extra protons, 2 extra protons. So the blue is a positive 2e. But when you touch them together, what happens is those electrons essentially spread out from each other as far as possible. And they can do that because we're talking about conductors. They can move easily back and forth through any of the atoms onto either conductor. And so they basically, because they're repelling from each other, just spread out as far as possible. And so when we're done, you end up having the same sigma charge or sigma q on each object. since my system had a sigma charge of overall +8 before, afterwards I have the same overall +8, but it's going to be distributed 4 and 4 instead of 6 and 2. So you could describe what's happening here. The red object is becoming less positive because it's actually gaining a couple electrons, and the blue object is becoming more positive because it's losing electrons, but the overall system maintains its charge. Now, a couple notes for AP. You're not asked to do this quantitatively, but you do often get questions on the MCQ about what happens if the objects are not the same sizes. Well, it's essentially the charge per surface area that's going to be the same. So if I had a tiny object and a big object, the electron spacing ends up being the same, but that is going to mean that the sigma q is bigger on the big object because it has more space for those electrons to go. So it's not always going to be exactly the same unless the objects are identical. One further note that they don't usually ask about, but the shape actually matters too. Certain shapes tend to have a higher charge density distribution. Pointy shapes can hold a lot more charge than flat shapes. You don't need that in this class, but it's kind of a fun thing to be thinking about as you move forward. Before we talk about the last mechanism for charging, I want to talk about one of the processes, which is grounding. So grounding, which you've probably heard of before, well, hopefully not at home with your, hopefully you didn't get in trouble and get grounded. This is a different kind of grounding. But this means you're basically connecting any object to Earth, or the ground, with a conductive wire. And what happens when you do that is you provide like a pathway for electrons to either flow to the Earth or from the Earth. We view the Earth as this unlimited source or sink. So source means it can provide the electrons, and sink means it can absorb the electrons, because it is so big and it's a conductor, and it's basically like infinite number of possible electrons. The way it physically happens, like in your house, is that they take a wire and they drill it into the ground. It's that third little wire in your plug, if you've ever wondered about that. And somewhere in your house, that wire is connected to something that goes out of your house and is drilled into the Earth, which is kind of cool. But we can ground objects in less complicated ways as well. Taking any kind of wire and connecting it to anything that is connected to the ground works as well. So, you know, I'm conductive. If I touch a charged object and my feet are touching the ground, that's going to be a grounding process where electrons either flow from the Earth through me to get to the object, or from the object off of me to get to the ground. When you get a static shock, this is often what is happening, is you're acting like a ground wire, and that's why it hurts. So the third charging mechanism is called induction charging. And we actually need polarization and grounding, and I know I haven't talked about polarization yet, but I'll do that in the next slide. And use both of these processes together to end up giving a sigma charge to a conductor. This is definitely the most complex grounding or complex charging mechanism, and also the most kind of industrially useful, because the objects don't have to touch each other. Unlike friction charging, contact charging, where you have to actually be rubbing and touching things, induction charging can happen even without contact. So you start with your neutral conductor, and you bring a charged object nearby to that conductor. So in this case, they brought a negatively charged rod nearby, and it doesn't matter if that charged rod is a conductor or an insulator, so you could have gotten that charged either through contact or through friction charging. When you do that, the original conductor is going to polarize, and I'll go into the details in the next slide, but you can see what's happening here essentially is that because it's a conductor, the electrons in that object are going to move around. That picture is not great because it kind of shows the protons moving. Those protons did not move to the left. What happened is their matching paired electrons moved to the right, and so we're left with just protons on the left. Not that they moved, but that they were kind of abandoned by the electrons who moved far away from that negative rod. So in any case, this is called polarization. We've got basically a separation of charges. The conductor in the middle is still neutral, but it has a negative half and a positive half. And that's sort of the basis of what polarization is. But the third step in the charging process now is to ground the conductor. So we talked about this, connect that wire from that conductor to the Earth. And in that process, electrons move on or off. In the example shown here, electrons are going to move off of it. And the reason is not because they're attracted to Earth, right? Earth's neutral. It doesn't care, but they're repelled from that negative rod. Okay, so because that negative rod is there basically pushing the electrons away, they use this as an opportunity to get far away from that negative rod and go off. If that rod was positive, the opposite would happen. Some of the electrons from Earth would say, ooh, there's a big, awesome positive rod up here. I'm going to zoom on from the grounding wire onto the charged object. So this can happen in either direction. Step 4 is to remove the grounding wire. And then step 5 is essentially to remove your charged object, the one that you brought in from outside. And now you're left with a conductor that has an unbalanced sigma charge because we took the electrons off and we're left with a positive charge. And finally, in point E, right, the charges end up being evenly distributed. If we pulled off 4 electrons, the electrons that are left are going to spread out evenly, so that the lone protons would be evenly distributed as well because the electrons are going to evenly distribute on that surface. So again, protons are not moving. This is all done through the movement of electrons. But there we go. We didn't have to touch the 2 objects to each other. We've created a charged conductor through the process of induction. So I mentioned the basics of the polarization process in the last slide, but it's a really important process that has other applications and not only happening during induction charging, so I want to go into a few more details. As I mentioned, polarization is using an object with a positive or negative sigma charge to push or pull the electrons in nearby objects, resulting in a positive half and a negative half. So for example, if I bring a big negatively charged object near a neutral object, what's going to happen is the electrons in that neutral object are going to be pushed away from the side, to the side furthest away from the negatively charged object while remaining neutral. So we now essentially have a positive half on the left and negative half on the right while still being neutral overall. One of the interesting effects of polarization is that the polarized object is actually going to end up being attracted to the charged object despite the fact that it's neutral. And the reason for this is the positive half is going to be attracted because it's oppositely charged from the negative half, and the negative half is going to be repelled. But the negative half is farther away from that negative object than the positive half is. And because distance has an inverse squared relationship with force, that makes a difference overall in the net force between these objects. So we have a stronger pull than we do a push. And that means overall, this neutral object is being attracted. And this will happen whether we're polarizing positive or negative. You should go through it both ways. But we see this a lot in the real world, and we'll do some examples in class as well. Okay, please take a minute to revisit the essential question. How do objects end up with an unbalanced sigma charge? What are the mechanisms and the processes that you need to understand when it comes to understanding this? Thanks for watching.